All right, so welcome to our new type of class. We're talking about organic chemistry. Now we're doing it virtually because of a virus. But one thing you'll notice about the organic chemistry section in general, it's going to be a lot different than anything we've done up to this point. So organic chemistry talks about basically anything that has a carbon in it. Right, so carbon is going to be like the central point of everything we're talking about now. So organic chemistry is the study of compounds that have carbon, and they can have just carbon with like a couple hydrogens on it, or they can be, 100 different carbons all connected to each other, and we'll look at a wide variety of these molecules, in the rest of the class here. So organic chemicals are all over the place, in our foods, clothes, all kinds of things like that. The coronavirus that is disrupting our lives now is an organic molecule or has organic molecules associated with it. And these can be, from natural sources like cotton and wool and other things. They can also be synthetically made in a lab. So organic molecules can come from all over the place. All right, so here's just a couple examples. Methane, which is like the main component of natural gas, stuff that you cook with, that's an organic molecule. It's actually CH4. All right. Ethylene is something that you see all over the place. That's like it's a starting material that's used for making polyethylene, which is basically a whole bunch of ethylenes connected to each other. And we'll look at kind of forming these polymers later on in the next chapter. But again, these are really common molecules that you see pretty much every day. All right, so let's look at some common features of organic molecules. So again, almost all organic molecules are going to have carbon, and most of them are going to have hydrogens as well. So an important thing here, all right, so carbon is always going to form 4 covalent bonds. So whenever we're looking at organic molecules, they're always going to be covalent molecules, so they're not going to be ionic. So they're going to be covalent molecules, which if you remember, covalent means electrons are being shared. All right, so electrons are shared in covalent molecules. So if you look down here at methane, it's written in 2 different ways. So the one that's circled there, methane, it's showing the dots for the electrons, and basically one of those electrons in each pair comes from hydrogen, 1 electron in each pair comes from carbon, and they're going to share those to form this same structure here, just written a little bit differently, where each of those lines is a bond for 2 electrons. And again, this part should all be reviewed for you guys. All right, so carbon always forms 4 bonds. Hydrogen always forms 1 bond. It's like hydrogen's one of the exceptions to the octet rule because it only has 1 electron to share. All right, so carbon can form single bonds, double bonds, triple bonds. And we've actually looked at these in the past whenever we were drawing Lewis structures. So just a reminder that carbon is always going to have 4 bonds, but sometimes you can have 2 of those bonds there in a double bond. Sometimes you'll have 3 of the bonds there in a triple bond. So in all of these, whether you're looking at ethane, ethylene, or acetylene, in all of those cases, each carbon still has 4 bonds, right? So in ethane, it has 1, 2, 3, and 4. Here in ethylene, there's 1 and then 2. Those are the 2 for the double bonds, 3 and 4. So no matter what, you're going to have 4 bonds for each carbon. The carbons can be in a linear arrangement, like you see in propane on the left, right, where they're in a line. Over on the right, you can see it's called cyclopropane, and that prefix cyclo we'll actually talk about later on as well. But notice that the carbons are all connected in what we call a ring. In this ring, it's like a triangle. But the point is they're all connected to each other, and you can have rings of as few as 3 carbons, like we're looking at here, and up to hundreds of carbons can form a more complex ring. We'll see carbons mainly in ring forms, like from 3 carbons up to maybe, say, 6 or 7 carbons. 6 is probably the one we'll see the most. Okay. All right, so organic compounds can contain things other than carbon and hydrogen, even though that's kind of what we're going to look at for the first 2 chapters the most. Whenever you have something that's not carbon or a hydrogen, we call that a heteroatom. So something other than a carbon or hydrogen would be a heteroatom. The most common heteroatoms are shown down here. The ones you'll probably see the most are oxygen and nitrogen, and then the halogens. All right. Remember with these other atoms, the O, N, F, Cl, Br, I, right? All of them have very characteristic bonding patterns. And if you go back to your memory from chapter 3, like for instance, you'll remember oxygen always has 2 bonds and 2 lone pairs. And nitrogen always has 3 bonds and 1 lone pair. And your halogens, which are those guys there, they always form 1 bond and have 3 lone pairs. So the number of bonds plus the number of lone pairs is always equal to 4, or another way to say that is our octet rule, which says that everything is always going to have 8 electrons around it. And this is table 10.2, which is actually almost identical to a table we saw back in chapter 3 that described these common bonding patterns. And you guys should definitely know this. This is something you should be aware of. All right, so this is important here. Whenever we talk about heteroatoms, the most common heteroatom is going to be oxygen, probably, and the most common multiple bond that we see. So in addition to the single bonds, if you're looking at a multiple bond between a carbon and a heteroatom, is going to be a C double bonded to O, like we see right over here. So this is one we're going to see a lot of whenever we start looking at various organic molecules, and it's something you want to be able to pick out. So anytime you have a C double bonded to O, we call that a carbonyl. Carbon with a YL. That is C double bonded to O. All right, and then the carbon would always have 2 other bonds coming off of it, and the oxygen would have its 2 lone pairs of electrons. But this carbonyl group is going to be your most common multiple bond between that you see with carbon and a heteroatom. So again, it's just something you should be aware of and be able to pick out. And we're going to talk about a lot of other types of molecules that have a carbonyl group in them. All right, so that's kind of a brief intro to some of the organic molecules and some of the things we're going to be looking at. And now I want to take a little bit of time to talk about how we're going to draw some of these organic molecules, and we've kind of looked at it already. But the thing with these organic molecules is they can be drawn a lot of different ways, and there's not one right way to draw them. So for instance, a molecule we're looking at down here it says CH3, CH2, CH2, CH3. And that is a correct way to write, this would actually be called butane as well. So you can say butane, you could write CH3, CH2, CH2, CH3, and you could also write it out this way over here. And all of these representations are correct. What we call this one over on the right, we call that a condensed structure. So in a condensed structure, we basically take out all of the 2-electron bond lines, so all of the bonds, like that one, and 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 there, and there, and there. So those are all the different bonds. We get rid of all of them, and we basically are going to write it as CH3, CH2, CH2, CH3. Basically, you can see it in the shaded regions where you have a CH3 and then you have a CH2, then another CH2, then another CH3. And let me, maybe I'll do it here in green. All right, so there's a CH3, and then that part there is a CH2. There's another CH2, and then another CH3. So usually I just kind of read, from left to right, like go in that direction, and you find your CH3 and you just keep reading from left to right, looking at your groups. It gets a lot trickier depending on the molecule, but this is kind of in general how you would look for it. So basically the rules here is when you have a carbon bonded to 3 hydrogens, it becomes a CH3. When you have a carbon bonded to 2 hydrogens, it becomes a CH2. In general, your CH2s are going to be in the middle of a molecule, and CH3s are going to be on the end, because basically, remember, hydrogen can only have one bond. So let me pick another color here. So if I circle that hydrogen in blue, right, that hydrogen can only have one bond, which is going to be to the carbon it's already attached to. So we cannot add anything to the left of that hydrogen. So the molecule cannot keep going. And similarly, that hydrogen, there's nothing else that can get added to it, or really any other hydrogen that you see there. So generally speaking, these CH3s are always going to be on the end of your molecule because they're kind of like caps. Once you put that cap on there with a CH3, it can't grow anymore, and that molecule is basically done growing. All right. So the structure that you would see on the over here, we would call that a complete structure. So if you ever see something saying draw out the complete structure of something, it would be with all the bonds shown. And then this one over here is the condensed structure. Now the condensed structure can actually be simplified even more. And we'll look at that here in just a second. Now, in some of our cases, we're going to have molecules that, this is very similar to the one we just did, where you have a CH3 right here, and then you have a CH, but this time it's not a CH2 that's right next to it. So there's a CH3, and there's a CH, and then you have a CH2, which is going to be this CH2, and then you have a CH3, and then you have a CH3. But now the one thing that is left is that CH3 right there, which is this one. So generally speaking, you kind of read from left to right, and if you have any extra carbon groups going in, you draw that extra line in there. So we draw that extra line to a CH3. So that's kind of, in some cases, you'll see that extra bond line drawn in, and that's what you see in this particular example. Now, I mentioned that sometimes condensed structures can be condensed even more. And the idea here is that we can use parentheses to further simplify like groups. So if you read up here, parentheses around like groups. So in this case, we have CH3, CH2, CH2, CH3. These two CH2s in red, they're identical to each other. So what we can do is we can say, in other words, this is going to be CH3, then CH2 parentheses 2, because we have two identical CH2 groups, and then another CH3. And a lot of times I'll get asked a question saying, well, can we just write, I'm going to come up here and draw something. Can we write CH3, 2, CH2, 2? Right, because there are two different CH3 groups here. And the answer is no, you cannot do it that way. And the reason is because those two CH3s are on opposite ends of the molecule. So you can only use the parentheses around the CH3s if they're identical to each other in terms of what they're connected to, which is going to be an example like we'll look at over here, over there. All right. So, but coming back to this one and why this is wrong. You want to be able to read your molecule from left to right. So if we were to do up here and say CH3, 2, you don't write two CH3s before you get to the CH2. All right, so that's a little bit tricky there. But again, the condensed structure with the parentheses around the CH2 there is appropriate. Now, coming over to the other side. Now, in this case, you do have a CH3 parentheses 2. So, in this case, this CH3 group and that CH3 group are identical to each other. And the reason I say they're identical to each other is they're both CH3s bound to that carbon where I have an arrow pointing at, which is a CH. So I'm going to underline this CH right there. Right? So that carbon, or CH, is attached to two identical CH3 groups. So we'll number them 1 and 2. Right? Those two are identical. Right? So 1 and 2 go there. And then you can kind of read from left to right throughout there. So the fact that you have a CH3-2 right there means you have two identical CH3 groups. They're both CH3 and they're attached to the same carbon, which is going to be the carbon right next to them on that linear structure. All right, so that, again, this is probably one of the more confusing things about drawing the structure is the fact that you can draw the same structure a bunch of different ways. And unfortunately, that's just how it is. So you have to kind of be able to read them and kind of understand like how to go from one to another and be able to recognize them. And you'll be able to look at and we'll go through some practice problems on how to do this, and like anything else, the more practice you do, the better. All right, so we'll get the hang of it eventually. So here's a couple practices, and what we'll do first is take these complete structures and draw condensed structures from them. So for the first one, you read from left to right. So I'm going to go here, I have a CH3, so I'm going to write CH3. And then I have a CH2. CH2. The next to it, I have a CH2. And I write a CH2. Then I have another CH2. And then I have a CH3. So that's one way I can write it. Now, the other way I could write it would be to say CH3. And I could do parentheses because I have 3 CH2s in a row. So CH2 parentheses 3. And then another CH3. Right, so those two are identical. They're both correct. All right, now let's go to the one on the bottom, which is a little bit trickier. But again, just because it's more complex and has more to it doesn't mean we do it any different. So we're going to start with the CH3 right there. CH3. Attached to it, we have a CH2. Attached to it, we have a CH2. All right, now attached to that, we have a carbon, and that carbon is attached to a carbon above it, a carbon below it, and a carbon to the right of it. So in this case, there's no H's attached, so all we do is write the C. So we just write that C. And then we can write the CH3 above it and beneath it. And this is one of those cases where, and I'll draw little clouds around them. Right, so those are the ones we don't write linearly because it's kind of apart, distinct from that linear chain that we're looking at. Okay, now keep moving to the right. Next we have a C that's bound to an H and the Cl. So what we're going to do is we're going to write the CH in our chain, and then we're going to say that that C is bound to a Cl above it. So basically, anytime you have a heteroatom, again, anything that's not a carbon or a hydrogen, you draw it out with a line to it, okay? Whoops, hit the wrong button there. All right, then after that CH, the last thing we have here is a CH3. Then we'd write CH3. And again, we could simplify this one a little bit more because we do have two CH2s next to each other. So we could also write this CH3, CH2, 2, C, CH, CH3 with a CH3 up there, CH3 down there, and then a Cl right there. All right, so again, two different ways you could write it. Both of them are correct. There you go. So now I want to do a couple more practices where we go from the condensed structure out to the complete structure. Oops. There we go. All right, so now this first one's going to be kind of easy, and the one on the bottom is going to be harder. So let's go up here. So CH3, Cl3. So you're going to start with a CH3. CH3. And then remember, carbon always has 4 bonds. The 4th bond is going to be to the carbon that's next to it. And that carbon needs 4 bonds, so it has 1 already, and then the next 3 are all going to go to chlorines. So chlorine, chlorine, and chlorine. And technically these chlorines would have an octet, remember? So they would have all of those lone pairs of electrons. All right, so that would be it for that one. All right, now the one on the bottom is a little bit trickier because notice we have parentheses, we have 2 sets of parentheses, but we can still do this one. So here we go. We're going to start with a CH3. CH3. Now CH2 4. That means we're going to have CH2 4 times in a row. 2, 3, 4 times in a row. Then we have CH and then CH3 So CH. Now remember that carbons have to have 4 bonds. So now the question is, what else is that carbon there bound to give it 4 bonds? We know it has a hydrogen, that's 1. We know it's bound to this CH2 that's over here, so that's 2. So where are the other 2 going? Well, that's where these come in, where it says CH3. So what's going to happen here is that you're going to have one bond that goes to a CH3, and then another one that goes to a CH3. So those 2 CH3s that are in blue here, this would be one of them, and then this would be the other. So again, whenever you have a CH3 that's in parentheses with a number, those 2 CH3s are always going to be bound to the same carbon. In this case, they're bound to that carbon, right? So that carbon there. All right, so that's kind of a brief overview of kind of what organic molecules are, and then kind of a beginning on how we're going to draw some of these molecules.